So in the last section you learned that logarithms are really just the inverse of exponential functions, or that you can use a logarithm to undo an exponential equation. There are some rules for logarithms that actually will help us accomplish this. The first thing that you have to pay attention to is that the base must be a positive number, meaning that if we're taking the log of base -5, this actually doesn't work. The next thing is that what you're taking the log of also has to be a positive number, so you cannot take the log of a negative number. So when you're taking log of some base of two values being multiplied together, what you can do is separate them as two separate logarithms. They have the same base, and then you add them together. Similarly, if we're taking the logarithm of two things being divided, we separate them and we subtract. Now, in the event that your denominator is a product, what you would end up having to do is say minus parentheses, everything added together, close your parentheses, because you would then distribute that negative. Another option to think about it is that anything on the denominator you have to keep putting minuses. And then finally, if we've got something to a power, what we can do is take that exponent and bring it down in the front, like this, and now we're taking the log of just a single value. Like many things, these are a lot easier to see than to just hear about. So we're going to express logarithm base 10 of A, logarithm base 10 of B. So what I do is I do these in steps. The first step is to say the logarithm base 10 A squared plus the logarithm base 10 square root of B. Now I know square root of B is really an exponent, so I'm going to remove that and say B to the 1/2 power. Now I use the third rule and take these exponents and move them out into the front. So what that does for me is it gives me 2 times the logarithm base 10 of A plus 1/2 times the logarithm base 10 of B. And that's going to be our answer. Taking a look at the next one. Again, I always start writing out the most simple form, and I do these in steps. Logarithm base 10 of A to the 5th. I'm dividing, so I subtract. Logarithm base 10, the square root of B cubed. Now again, the square root of B cubed, I'm going to do off to the side. That's B cubed to the 1/2. Power of a power, I multiply, so really I've got the logarithm base 10 of B to the 3/2 power. Now I take my exponents and I move them out to the front. So I get 5 times the log of base 10 of A minus 3/2 times the log base 10 of B. We can also go backwards when we do this, and in that case, we're really just going to reverse what we're doing. So what I notice here is I have a subtraction. I also notice that all of this is over 2, which tells me that I'm multiplying this whole thing by 1/2. So the first thing I'm going to do is rewrite this. I have 3 log base 6 of M minus 1/2 log base 6 of N. Now I'll take these values that are in front and move those to the exponents. So I have log base 6 of M cubed minus log base 6 the square root of N, because N to the 1/2 power is the same as the square root of N. Now that I've got that, I now have the more simplified form here that I can make into a quotient. That I have log base 6 of M cubed over the square root of N. And even though we've got all those rules about square roots in the denominator, when we're dealing with logarithms, we'll accept it. We can use the same technique to solve. So I've got log base 5 of x, and I'm going to take this whole right-hand side, and I'm going to simplify that so that I have it written as simply one logarithm. So that's equal to log base 5 of 2 cubed, right? So I took that 3 and I moved it to the exponent, plus log base 5 of 7. Now what I see is I've got the same base and we're adding, so I can make this log base 5 of x equal to log base 5 of 2 cubed times 7. Well, I know what 2 cubed times 7 is. Two cubed is 8. 8 times 7 is 56. So this gives me 56. The next thing that you need to remember is that if you have the log of the same base, then whatever you're taking the log of, that's going to be equal. So in this case, x is equal to 56. Not 5x, 56. Taking a look at the next one, we're going to go through the same process. Now, one thing I want you to pay attention to, see how these are added, this is subtracted. A lot of you are going to want to distribute this logarithm. You are not allowed to do that. You cannot distribute a logarithm. It's like distributing a square root. You can't do it. So you're going to have to find another way, and that way is to recognize that this is being added, which means that I can multiply these together. So I end up with the log base 7 of x plus 1 times x minus 5 is equal to 1. So that's x squared minus 5x plus x, that's minus 4x minus 5 is equal to 1. The next thing that you do is going to seem very unusual, but it's something that you did in 10.4. You rewrite this logarithm as an exponent. Base, there's your power, your exponent, and that's what it's equal to. So what that tells me is 7 to the first power is equal to x squared minus 4x minus 5. 7 to the first is equal to 1. I can subtract 7 from both sides, and I'm going to flip-flop this around because it makes the most sense to me. X squared minus 4x minus 12 is equal to 0. So now I can actually work with this, and I factor because I know how to factor. And I know how to solve this. I get x is equal to negative 2 or positive 6. Now the most important thing. I do have to plug this back in to check. So if I have the log base 7 of negative 2 plus 1 plus the log base 7 of negative 2 minus 5, what I get here is I get the log of a negative 1 and the log of a negative 7. I can't do that, which means that negative 2 isn't possible. I can try it again. Log base 7 of 6 plus 1 plus log base 7 of 6 minus 5 is equal to 1. So that's the log base 7 of 7 plus the log base 7 of 1 is equal to 1. Well, log base 7 of 7 is 1. And we're running out of room, so I'm going to move up here. Right, log base 7 of 7. Well, so it's 7 to what power is equal to 7? So this one here is 1. And then the log base 7 of 1 is equal to what? So 7 to what power is equal to 1? To get 1, you need a 0 power. So that's 0. And 1 plus 0 is equal to 1. So the answer here is that x is equal to 6. So the next section, really all we're going to look at in this section is the change of base property. And what that means is that if we are given the logarithm to some base, we can actually change the base of our logarithm. The reason that we want to do this is because in our calculator, that log button is what we call the common logarithm, and it's log base 10. So we don't have to write base 10 every time. We can just write log, and it's called a common logarithm. So we would use this so that we can convert anything to a common logarithm, and then we can just plug it into our calculator. You may be thinking that you're pretty sure that the calculator does something like this without your knowledge or without your needing to know this, and that's fine, except that there's probably going to be a question like this on the non-calculator part of your test. So be aware of that. So let's start with a couple of common logarithms. Log that's base 10 of some number is equal to 3.7135. So what that means is 10 to the power of 3.7135 will be equal to x. This is a calculator problem. You find out that x is 5,170.113. Well, you do the same thing again. Here it just says log. With no base is written down, I know that it has to be base 10. And again, I can see that we've got 0.00352 will be equal to x. So I've decided I don't want you to do the 4th root of 38.2. Instead, I want you to do 4 to the power of x equals 50, because you need to know how to solve these. What you are allowed to do, just like you're allowed to add something to both sides or subtract something from both sides or take the square root of both sides, you're also allowed to apply a logarithm to both sides. So I'm going to take the logarithm base 10 for x to the power of x is equal to the logarithm of 50. Now I use my rules of logarithms, and I move that out to the front. And now I've just got a product, so I can divide by the log of 4 on both sides. And once I'm here, this gets put into my calculator. Once I put that into the calculator, I find that x is equal to 2.822. Taking a look at the next problem, we'll do the exact same thing. Okay, I will just apply a logarithm to both sides. So I'll take the log of 2 to the 3x is equal to the log of 7. Then I use my rules of exponents. I take this and I move it out to the front. So I get 3x times the log of 2 is equal to the log of 7. Then I divide both sides by 3 times the log of 2. Now why do I multiply by 3 times the log of 2? I do that because I want to get rid of that 3 and the logarithm. So on the left-hand side, I'm left with x is equal to 936. Now what I want you to pay attention to when you enter this into your calculator, you're going to enter log, and the parenthesis is going to show up, so log of 7. Then you'll hit divided by. Then you need to open your parentheses for the 3. Log, open parentheses will show up. 2, close your parentheses twice. Remember that you have to show that this whole thing is the denominator not just the 3, so you need to have parentheses around it. Let's take a look at the last problem. This is where we will use the change of base formula. Using that formula, I'm going to choose to use base 10, because if I have base 10, I can plug it into my calculator. So I'll have log base 10 of 5 divided by log base 10 of 3. I enter those into my calculator, and I get 1.465. The way to remember this formula is I think about this number that's tiny, sort of on the bottom, stays on the bottom. The bigger number will move up.